Okay. Okay, so hello everyone. Welcome to another session of the Prebiotic Chemistry and Early Earth Environments seminar series. My name is Danielle Simkis, and I'm one of the seminar co-organizers along with James Iguchi, Becca Guth-Metzler, and Albert Fehrenbach. For those of you who have not attended a PCE3 session before, these seminars take place every 3 weeks. And the motivation for having these sessions is to facilitate discussions among prebiotic chemistry and early earth research. This is also an opportunity for us to highlight all of the exciting research that is being carried out by our talented early career researchers. So today's guest speakers are Dr. Rachel Smith, Lucas Smith, and Danna Qasim. And we will start the session off with a short topical introduction from Rachel Smith, followed by presentations from Lucas and Danna. And then once the 3 presentations are over, we'll move on to the Q&A portion of the session, at which point we'll open up the chat and you'll be able to type in any questions that you may have for the 3 speakers. We will also have the opportunity to continue this discussion after the seminar through our PCE3 Slack group. So if you have not already joined that group, we'll be posting a link to the Slack group invite so you can sign up and continue the science dialogue after today's session. So with that, I think we will go ahead and we'll get started with today's presentations. So to start off, we'll have a short introduction from Dr. Rachel Smith. So while Rachel is getting her slide uploaded, I'll do a quick introduction for Rachel. So Rachel is an astronomer specializing in forming stars, particularly the chemistry of carbon and oxygen in protoplanetary disks and how these chemical pathways connect to the early solar system. She primarily uses large ground-based telescopes to observe a range of star-forming environments across the galaxy. Rachel is head of the Astronomy and Astrophysics Research Lab and curator of meteorites at the North Carolina Museum of Natural Sciences in Raleigh, North Carolina. She is also an associate professor in the Department of Physics and Astronomy at Appalachian State University and adjunct professor at UNC Chapel Hill. With that, please feel free to get going.
Thanks, Danielle. Can you hear me okay? Should I, let me know, just shout and interrupt if I should do something else. But hey, everyone, thank you for coming. It's a nice big group. So I'm going to do a short introduction, as Danielle mentioned, for the first talk by Lucas Smith, who was worked with me on an Emerging Worlds grant from NASA, funded by NASA, that was looking at trying to do experiments with interstellar ice analogs to investigate some unusual isotopic signatures we were seeing in some YSOs that I use ground-based astronomy, as Daniel mentioned, to observe. So I will do that. It'll be hopefully 5 minutes. So first of all, my cat, if you hear me meowing, that is my cat. I apologize. He comes in for all my Zooms. So first of all, if you don't know, what we do with ground-based astronomy with observing in absorption, we're looking at CO in absorption, which basically very quickly, I'll just say, gives you, enables you to get really precise isotope ratios from CO. And so looking at carbon, 12C, 13C, and sometimes oxygen, if we can actually observe that, and the weaker oxygen lines like from C17O and C18O, so 18O and 17O are a little harder to observe, and that's kind of a separate study from the one that Lucas will talk about today, which focuses on carbon. And we're looking at a single sight line, so obviously not to scale, but these are little CO blobs that I put in. This is IRTF, the infrared telescope facility on Mauna Kea, where we observe in person, if we can. COVID put a little wrench in that, but have done several observations there. And looking through these, through the disk gas of protoplanetary, of massive YSOs, as well as some mass YSOs, depending on how bright they are. And with absorption, we can get precise isotope ratios from the CO, and I won't talk about that analysis so much, but I will talk about some of the results. And first of all, we can, along this single sight line, we can get abundances in the same, we assume in the same environment by virtue of the temperature of the gas. So in cold gas, we'll see CO, we'll sometimes see related to that CO ice, which of course colder, but is in the same general cold gas environments, like an outer disk or an envelope possibly. And then also compare to some CO2 ice, which is hard to get. Some of you probably know it's hard to get abundant, the abundance is right for not having too much or too little for the 12 CO2, 13 CO2, but there is some data out there published by my collaborator, Edwin Bogart, who looked for some of these same targets. And so we can look at carbon in CO2 ice as well. And again, this is with Keck. We have some Keck observations, just looking along the single sight line to compare with different reservoirs of carbon. And just quickly, I'll say we found this heterogeneity. So this is 12C, 13C on the y-axis, and on the x-axis is galactocentric radius. So this would be like the galactic center, and we're kind of here in the blue, in the yellow, at about 8 kiloparsecs in the yellow diamond. And we see this kind of this heterogeneity, and a lot of this is low mass stars. I don't have the one, it was a little complicated to keep, to put on lots of plots is for 5 minutes, but I'll just mention that we see this also in massive YSOs, this kind of really this unexpected spread of 12C, 13C. And we wanted to explore this further. The data here were collected with VLT cryoris, which is very high resolution, also very accurate, we think, and precise. And we tested these the method of deriving these abundance ratios and think they are correct, and they've been published in some papers already. And we're working on the massive YSO set right now. But one thing that we wanted to look at is, can we compare CO ice to the 12CO, 13CO in the gas and see if there's any kind of correlation? Maybe the ice has something to do with the spread in the 12CO, 13CO in the gas. And we did some targets that had CO ice observations and saw that, it's kind of a splatter, but there could be some correlation, and it's worth investigating. Can we look at fractionation in the CO ice to see if we get some kind of heterogeneity in the gas? And maybe there's something going on with the 12CO, 13CO in the ice that influences the gas phase ratios. And that's where these experiments come in. And we were funded, I have, I'll put the acknowledgement on the next slide or two, funded to do these observations in Dr. Murthy Gudapati's lab at JPL, and also funded, it's interdisciplinary. There were some models that didn't actually show a lot, but also observations. And so it's an integrated project to look at this fractionation and see if we can understand something better about carbon chemistry by looking at these experiments and trying to explain what we see in the gas phase. And so this is Robert Lewis, who was, Lucas was an undergrad at the time at App State, and Robert was also an undergrad, and they went to JPL. Lucas went to JPL 3 summers in a row to do these experiments. And this is that CO ice plot again. This is my second to last slide. What's been found, and this has been accepted in astronomy and astrophysics and is in press, is seeing that there is a consistent 0.1 Kelvin temperature difference in sublimation of the gas. And so it seems that from these experiments, it looks like there's a preferential desorption of 12CO instead of as compared to 13CO, and that 13CO could be held tighter by the higher binding energies in the CO. And so that's what Lucas will talk about, are those experiments looking at the binding energy differences between 12CO and 13CO, and these are actual results from his paper, his first author paper that was just accepted at ANA. And then the last slide, this is our grant, and thank you very much to NASA for this. And this is why I'm part of PC3. And this is the paper is submitted, is looking at photodesorption differences and seeing how photodesorption is photodesorbs consistently or really 13, but that again is explaining these binding energy, what we see in the temperature differences in the sublimation. And so it looks like from these experiments, we actually found a significant difference between 12CO and 13CO, and that 13CO could be held much more tightly in the ice phase, which would help explain some of our observations. And that is all I have. I hope that was more or less 5 minutes. And now it is Lucas's turn to tell everyone about his experiments. Thank you.
Great, thank you, Rachel. You broke up a little bit in that last slide, but I think.
I was just saying the last slide was about the photodesorption looking at photodesorption to help explain the what we think are binding energy differences in the 12CO, 13CO. So those photodesorption plots, hopefully Lucas will expand on those, and those are we're preparing those for AppJ. So
okay,
that's all.
Great. Thank you so much.
Thanks to my grant, by the way. To the NASA. That was acknowledging the NASA grant. Thank you. So
great. Thanks.
Lucas
okay,
is up.
So we'll move on to Lucas's. So just as a quick introduction for Lucas, Lucas attended Appalachian State University for his undergraduate studies, where he earned a Bachelor of Science in Physics in 2015. While at App State, he was a student researcher working with Dr. Rachel Smith, during which he studied the desorption of CO ice under Dr. Murthy Gudipati at NASA's JPL laboratory. Sorry, one moment. Lucas is currently working towards a PhD in planetary sciences at the University of Arizona's Lunar and Planetary Laboratory, where he studies pre-solar stardust and organics and carbonaceous chondrites analogous to asteroid Bennu. And with that, you can get started.
Awesome. Thank you for the introduction. And Rachel, thank you for going over a lot of that background. That'll, I think, make things run a little bit more smoothly. But yeah, so I'm going to talk about the experiments that I did at JPL, working with Rachel and Murthy on Rachel's Emerging Worlds grant, where we investigated two different methods for possibly fractionating CO isotopologues between the ice phase and the gas phase. So hold on, it's not letting me advance my slides. There we go. Okay, so I'm going to start off a little bit with why were we interested in carbon monoxide in particular. Well, it's extremely abundant. It made up about 30% of the carbon and 10% of the oxygen in the early solar nebula, and is the second most abundant molecule in the universe, but also in protoplanetary systems and the interstellar medium. And on top of that, it's easily accessible through IR observations, as Rachel was talking about. So that makes it a very good evolutionary tracer of what's going on inside of molecular clouds and protoplanetary disks as they evolve. Furthermore, CO is an important prebiotic molecule. Under the influence of radiation with molecular hydrogen, it can form more complex organics like formaldehyde and then et cetera, so on. And then what's interesting about it is because CO is so volatile, which I will talk about with the thermal desorption experiments, when in a protoplanetary disk, it can only really exist in the ice phase towards the outer edges of the disk. But this carbon chemistry can cause it to the carbon from the CO to be trapped inside of less volatile molecules. And as things move around radially within the disk as it evolves, it provides a means of getting this this ice phase and solid state carbon from the outer disk and into the inner disk. So that's another reason why these isotope ratios and fractionation are so interesting, because the radial transport of the solids can influence what comes into the inner part of the solar system. So to kind of summarize all of that, it's obviously very important to understand how carbon evolves in these systems if we want to fully understand solar system and planet formation. So this is the heterogeneity that Rachel was already talking about with these plots. I'm going to go ahead and skip through these. I wasn't sure how much of this she covered, but these interactions that she was talking about between ice and gas phase, where there's that possible fractionation resulting from the isotope ratios of CO in the ice and gas phases influencing each other, that serves as the motivation for these experiments. So our approach was to take two different sort of processes. There's the thermal desorption, which is sublimation. It's just a heat-induced phase change from ice to gas. And then there's photodesorption, which is the absorption of a UV photon inducing a phase change. In order to do this in the laboratory, we need to be able to simulate conditions within these disks in order to get sort of relevant and accurate data. So the chamber that we work with, the Himalaya, is capable of getting to near astrophysical temperatures and pressures. We simulate CO being frozen out onto dust grains by forming CO ice onto solid sapphire within the center of the system. And to simulate the radiation, particularly Lyman alpha, we use a hydrogen discharge lamp. So for the thermal desorption experiments, the primary goals were to constrain the sublimation temperatures of CO for both 12CO and 13CO, and determine if there are any binding energy differences between the two isotopologues. And two methods involved in this. You can either heat the samples up constantly or incrementally and leave them at each temperature for a period of time. So I will get into the benefits of both and how we ended up using both. And then for the photodesorption experiments, we were looking for whether or not 12CO would be preferentially released from the ice phase over 13CO in the presence of UV radiation. So this is an image of the Himalaya. I have on the next slide a schematic so you can actually see where all these instruments are that I'm going to talk about, because it's everything's kind of too close together and white on a white floor, so it's kind of hard to put labels on this, but the Himalaya can get down to 10 to the minus 10 millibar and 4.2 Kelvin, which is certainly adequate for simulating these near astrophysical temperatures and pressures that I was just talking about. In order to measure the solid ice in the sample, in the chamber, we use Fourier transform infrared spectroscopy. And to measure the gas phase that's desorbed off of the ice, we use mass spectrometry, specifically a quadrupole mass spectrometer residual gas analyzer, but I'm just going to refer to it as QMS because that's much easier. So that's how we quantify the molecules that are released from the ice, and also keep an eye on any sort of contamination, whether it be atmospheric leaks or like residual cleaning from ethanol within any of the tubes that's in the chamber. So make sure our samples are pure. And then the other key component is the hydrogen discharge lamp, which we use for the photodesorption experiments. So this is a much easier to understand view of the Himalaya. This is top down, and the window in the center is made of sapphire, and that's where we grow the CO ice. There's the gas inlet tube that's oriented 90 degrees to the window so that as much of the gas that's coming into the chamber freezes onto the window as possible, and as little freezes on the edges and tops of the chamber. Because the FTIR, as you can see, is passing directly through the window, it's detrimental to our data if we have a bunch of CO freezing out on the windows of the chamber and other places, because as the temperature increases, that's going to produce the effect of gas phase molecules being detected that aren't being detected through the FTIR. The QMS, the mass spectrometer, is directly opposite of the inlet tube. And then the only difference between the two schematics here is the presence of the UV lamp on the right side during photodesorption experiments. And since both of these experiments I'm going to talk about use samples that were formed in the same way, I'm just going to talk about those in the beginning before I sort of split up the two, thermal and photodesorption, into almost their own separate little presentations. But we started off by taking a gas bulb that's viewed here and filling it externally on this system that we referred to as the multi-mixer in the lab. We filled it with either pure 12CO or 13CO gas in the case of the thermal desorption experiments. And then in the photodesorption experiments, we prepared isotopically enriched mixtures, whether it be enriched in 12CO or 13CO. And early on in the experimentation, we came across the issue of CO3 contamination in the chamber that was throwing off our sublimation temperatures, and our IR spectra was producing a large phonons band. And so this whole process of contaminants being removed was motivated off of that struggle that took away about 2 or 3 months of our actual time in the lab trying to figure this out. So we, on this multi-mixer, we had a cold finger that was submerged in liquid nitrogen before we opened the bulb up to receive the CO gas. So anything with a condensation temperature higher than liquid nitrogen would be frozen out within that cold finger, and that included CO3 and CO2 and any water that remained in as well. And then once we filled this bulb, we moved it back to the Himalaya and connected it to the line that was the gas inlet tube on the previous slide, where it was deposited on a sapphire window. And once we have the gas bulb set up, we would cool the system down to 20 Kelvin, take infrared and mass spec, This is one of the mass spectrum on the right side to make sure that we didn't have any contaminants in the chamber before we started depositing the CO gas. As you can see, by far the most dominant molecule in the chamber was molecular hydrogen, which doesn't interact with CO ice at these temperatures, so we don't have to worry about it messing up our sublimation temperatures. Once we collected these spectra, we would release the gas into the system at a partial pressure of 5 × 10⁻⁹ millibar and keep that going for 30 minutes. And then we would close off the gas bulb and take QMS and FTIR spectra to make sure that we didn't have anything that we didn't want in there. This is a QMS spectra taken during the deposition, so you can really get a much better idea here how much CO is coming into the chamber relative to anything else that might freeze out, which is really just water and nitrogen, but those are several orders of magnitude lower than CO. So our samples were okay, and they were not going to affect our data. And these ice films were about 200 monolayers thick, which translates to a couple hundred nanometers. So now I'm going to talk about the thermal desorption experiments. As cool as this video is in the background, this is unfortunately not from one of our experiments. This is just CO2 ice. I just added it for visual effect. But these are the experiments where we investigated the sublimation temperatures and the binding energies. And the binding energy itself is the energy required to make that transition from the ice to gas phase. And in the case of thermal desorption, that energy is provided through heat to the molecule. It's directly correlated with the temperature of sublimation. That's pretty intuitive. And the binding energy of these molecules is entirely dependent on the matrix that the molecule is embedded within. So if you have an ice sample that is pure 12CO, 12CO, that's going to have one binding energy. And then if you have an ice sample that's pure nitrogen ice, N2 is going to have a different binding energy. And then if you mix the two, you're going to have a CO and N2 binding energy as well. And this also applies for isotopologues, where 12CO binding energy is different from 12CO, 13CO binding energy, which is different from the 13CO binding energy. And we can determine the binding energy by using the Arrhenius equation, which relates the reaction rate, which in this case I'm going to refer to as the desorption rate, to the temperature and the binding energy. Here, nu naught is the pre-exponential factor, which is highly correlated with the binding energy, as you can see from the equation. So the challenge here is having a way to try and determine both the pre-exponential factor and the binding energy separately. And really the only thing you can do there is try and constrain one as best you can, and then use it in a different method to calculate the other. So these are just two forms of the Arrhenius equation. The linearized one on the bottom is also used for the Arrhenius plots that I will show later. And CO is what's referred to as a zero order reaction, so it's independent of the concentration of the CO. And this is the case for most of the sublimation process that we looked at. However, once you get towards the last couple of monolayers of CO ice, the reaction stops being a zero order, and that's because you start having binding energies between the CO and the substrate that they're on, which in our case is sapphire. And to get the desorption rate for a zero order process, it comes from solving a simple differential equation, which here is just the change in concentration over time. So that's very straightforward. And in these experiments, it's the concentration at one temperature and then concentration at the next temperature, and then the time elapsed between those two temperature readings. And to quantify this in the ice phase, we used IR spectra from the FTIR. We converted the transmittant spectrum into absorbance, obtained the integrated absorbance from it, and then the integrated optical depth of absorbance, and then finally to column density, which is N here. That's what we used as our final measurements. Our desorption rates for the ice phase are column density per second, change in column density per second. And the gas phase, we used the differences between two readings from the mass spectrometer over different temperature or time intervals, which correlate to different temperature intervals as well. And we needed to invoke the ideal gas law, which it actually works fairly well, even though this is really low pressure and low temperature. The tricky part is that the volume of the chamber, you can't treat it as a constant because you have constant pumping by the vacuum pumps. So you have to account for the amount of CO that is evacuated from the chamber during that interval between measurements. And as I mentioned before, we needed two methods to obtain the binding energy and the pre-exponential factor separately because they're highly correlated through the Arrhenius equation. So the first method is temperature programmed desorption, and this is the method that's been most widely used in the literature. And temperature programmed desorption involves a constant heating rate and then constantly monitoring the pressure changes with a mass spectrometer. The problem with this is you're moving really quickly. So in the case of CO, where its sublimation temperature range is actually very small, you can actually run past the sublimation temperature and ice will still be there momentarily, so it can throw off your readings of desorption rate at different temperatures. But in our case, we use temperature programmed desorption to sort of constrain the pre-exponential factor and then calculate the binding energies through the second method that I'll talk about. And another good check of doing temperature programmed desorption is, because it's been so heavily reported in the literature, we can compare what we get through TPD to literature values to make sure that everything is sort of okay in our system. And the method that we used to do TPD was the ice started out at 20 Kelvin. After we deposited, as I previously mentioned, increased the temperature to 25 Kelvin at 1 Kelvin per minute, and we left it there for 30 minutes. Then after that 30-minute interval, we started the actual TPD, where it's a 0.1 Kelvin per minute change in temperature, and we just let it keep going until all of the CO was gone. We continuously monitored this with the mass spectrometer and had the FTIR finish collecting a spectrum every 1 minute. So we have a spectrum for every 0.1 Kelvin change in temperature. And we did this with both pure 12 CO and 13 CO ice samples. And this figure on the right is just the straight pressure versus time data from the mass spectrometer. This isn't processed or anything. So you can see the slope of the curve is exponential up to a point, and then it kind of starts breaking down a little bit. And that's where it changes from being zero order to more first order reaction. And this red dashed line is the peak of the TPD curve, which indicates where all of the CO ice is desorbed, and then the curve starts to fall back down as CO is pumped out. And this pressure versus time data, we wanted to convert to pressure versus temperature, since we're trying to correlate desorption rate with different temperatures. So we just simply did this by taking the time that elapsed for each measurement in the the PV lowercase t, and then the heating rate to get a temperature. So these are effectively the same two plots, just with a different x-axis where it's converted to temperature instead of time. And then we would fit the data with an exponential growth curve, which models the zero order reaction process. We did this up to 30 Kelvin, where the dashed lines on this figure on the right end, because that's where it starts breaking down the zero order assumption. And the comparison between these two curves, we can see that even at the lower temperatures, where there's not a whole lot of desorption going on, that 12 CO has a higher partial pressure, which indicates that it's desorbing faster. And it actually, the PVT curves do end for 12 CO like just about 0.1 Kelvin before 13 CO, but the TPD method's not precise enough to give you an actual sublimation temperature from that. And to actually obtain the binding energies and pre-exponential factors using this method, as I mentioned before, we use the Arrhenius plots, which is linearized Arrhenius equation plotted with natural log of your desorption rate on the y-axis and inverse temperature on the x-axis. And if you fit a line to this, the slope of your line is your binding energy, and the y-intercept is your pre-exponential factor. For these TPD experiments, we both kept the intercept as a free parameter, which allowed us to get an experimental constraint on the pre-exponential factor and a binding energy in our settings. And then we also used fixed values of the pre-exponential factor. So we fixed the y-intercept for comparison with the values reported in the literature for their binding energies. And the second method is temperature interval desorption. And I'm going to talk about all the results of these two together at the end of this section, because if I started talking about TPD results already, it would be lost by the time we got to the end of the TID experiments that I'm talking about now. And it's important to keep those together. I just wanted to say that in case anyone was wondering where the results went. But so this is the method where we heat the ice incrementally. We called it temperature interval desorption. It had been reported in the literature before, specifically by two studies, one by Luna in 2018 and then Sanford and Amendola in 1993. But it utilizes the incremental increase in temperature, and then you leave the ice for a certain period of time before making your measurement. This is a much better method for obtaining the binding energy because your desorption rates have a much more accurate constraint on them, because you're effectively averaging your desorption rate over your equilibration period at one temperature, as opposed to instantaneously, nearly within about a second between two temperature intervals as you're constantly heating it. And so we use these TID experiments to determine the sublimation temperatures of 12CO and 13CO, and then also the binding energies through the Arrhenius equation by using the pre-exponential factors derived from our TPD experiments, which is very similar to what Luna et al. Did in 2018, except they did it the other way around. They used TPD to constrain the binding energy, and then TID to get a temperature dependence on the pre-exponential factor. And the methods for the TID, as before, once we had the ice on the window at 20 Kelvin, we would increase it to 25 Kelvin at a 0.5 Kelvin per minute interval rate. Then we would leave it there for 15 minutes, collect spectra, both FTIR and QMS, do the same thing to 27 Kelvin and 28 Kelvin at 0.1 Kelvin per minute. We left it for an hour there. And this was just to make sure that there wasn't any desorption between these two temperatures where we would miss a data point in our sublimation data. And at 28 Kelvin, after an hour, there was only the slightest amount of detectable desorption. So from then on, we moved in 0.1 Kelvin intervals at 0.1 Kelvin per minute heating rate every 30 minutes, with spectra collected at the end of each interval. And these are just both a bunch of FTIR spectra. On the left, it's from 12CO experiments using TID, and on the right, it's 13CO using the TID method. And this is just a good visual for how the abundance of the ice is decreasing throughout time, and then all the way down at the bottom, we see that there's no more 12CO left at 28.9 Kelvin and no more 13CO left at 29.0 Kelvin. So we took these FTIR data at each temperature interval. We would normalize the integrated absorbance to the initial integrated absorbance at 20 Kelvin. So it was giving us the change relative to 1, so we could compare between different experiments and between the two different isotopologues. So this is the sublimation curve on the right. We fitted them with exponential decay as it's a zero order process. This is a close-up from 28 Kelvin to 29 Kelvin. Here you can really see that there is a real difference in the sublimation temperatures and therefore the binding energies. we have 50% of this 12CO depleting at 28.6 Kelvin, and same for 13CO, except it's 0.1 Kelvin higher, and that translates over to the complete desorption temperature as well, where there's that 0.1 Kelvin difference in sublimation temperatures that Rachel was mentioning in her introduction. And to calculate the binding energies from these methods, as I mentioned before, we use the Arrhenius equation in this form. Absorption rate was determined between two temperature intervals over the 30-minute equilibration period. The values of pre-exponential factor we used from our TBD experiments and also those that had been previously reported. And we calculated our final binding energies as a weighted average over select temperature ranges. And the reason we picked these temperature ranges instead of going all the way from 20 Kelvin to whenever it was completely desorbed is between 20 and 28 Kelvin, you have effectively no desorption, or if you do, it's balanced out by redeposition of gas in the chamber. And towards the end of the sublimation, you're running out of CO ice, and you start getting that interference from binding energy interactions with the substrate itself. So we picked our temperature ranges to be right in the middle, where we had a significant amount of sublimation occurring, but we still had quite a bit of CO ice left.
Hey, Lucas.
Yes.
We're reaching maybe about 5 more minutes do you know how many more minutes you have till the end of your talk?
Well, in 5 minutes, I can finish the binding energies, and then I can just, in 1 minute, skim through the photodesorption.
Okay, just giving you a heads up that it's getting.
Okay, thank you.
Yep, no problem.
So this is a table from that paper that Rachel was mentioning that we just had accepted in astronomy and astrophysics. And this is summarizing the different binding energies and free exponential factors that we obtained through our two methods. In the purple circles off to the right, those are what we reported as our final binding energies. Those were obtained from the TID experiments using the pre-exponential factors we got from TPD experiments. And we can actually quantify a true difference in the binding energies here, which is the first time that's been reported. Previously, they were overlapping just by a few Kelvin, but with the TPD method, they have uncertainties between 15 and 25 Kelvin. So this is really the advantage of the TID method, is you get that significantly improved precision. And we were also able to determine that there was actually a larger difference in between the two, and that is actually statistically significant here. But when we used values reported in the literature for the pre-exponential factor with our TID data, we got significantly higher binding energies. However, our TPD experiments themselves were yielding comparable binding energies to what was reported in the literature, but slightly different pre-exponential factors. So this kind of highlights the importance of determining the pre-exponential factor and the binding energy under the same experimental conditions, because they are so interdependent on one another that using one to calculate the other that were determined under different conditions is going to yield drastically different results. So kind of just to summarize all of the thermal desorption data, so found a binding energy for 13CO to other 13CO molecules of 848 plus or minus 6 Kelvin, compared to binding energy for 12CO to 12CO molecules of 833 plus or minus 3 Kelvin. So the higher binding energy of 13CO indicates that it's more tightly bound in the ice phase than 12CO. So this is what Rachel was also talking about when there was potential interactions between ice and gas phases with small temperature changes, possibly influencing the isotopic composition of either the ice or the gas. So even just near 28 Kelvin, which is close to the sublimation temperature of both, you could have more significantly more 12CO accumulating in the gas phase and 13CO becoming enriched into ice. And additionally, the constant heating in TPD, as I was discussing, it leads to less accurate constraint of your desorption rates because of the short temperature intervals and the constant heating, which accumulates into your binding energies So our TID experiments with this average over a long equilibration period for the desorption rate leads to more accurate desorption rates and therefore better estimates of the binding energy. And our sublimation temperatures, they are within the error of each other. It's 0.1 Kelvin difference with uncertainties on each of 0.2 Kelvin. They do reflect different binding energies. And although we couldn't resolve this sublimation temperature difference with the number of experiments we did using the resolution of our temperature controller, it was consistent that every single experiment for 12 CO, no more ice existed at 28.9, whereas for 13 CO, there was still 13 CO ice at 28.9 Kelvin. So this difference could likely be resolved with increasing the number of experiments, but it was found systematically across all. So just to tie that all together, we determined the sublimation temperature and binding energies using the TID technique. The binding energies for the TID technique we obtained using exponential values obtained through temperature programmed desorption. And as a result of this, we found the first difference that is statistically significant observed in binding energies between 12 CO and 13 CO. And then again, despite having different nu naught values, our TPD studies matched with the literature, which goes back to what I was saying, where you need to determine both under the same experimental conditions. Otherwise, you're not going to get valid results. And then lastly, once again, the TID method significantly improves your accuracy of determining desorption rates and binding energy. So do I have any more time, Danielle, to go through the photo desorption in like 1 minute?
Yeah, 1 minute is fine. I'd say if you can stay within just a couple minutes, that would be great. Okay,
cool. So the photo desorption was the last thing that Rachel was talking about when she broke up. It's the ice to gas phase change induced by a UV photon. It's been proposed as an explanation for observations of cold CO gas in areas where the temperature should not permit CO to continue to exist in the gas phase. So it maintains CO in the ice phase or the gas phase by desorbing CO ice. It's non-wavelength dependent, it's non-thermal dependent, so there's no temperature dependency on the efficiency, but it is wavelength dependent. And the hypothesis behind our experiments was that differences between the 0 point energies of 12 CO and 13 CO may lead to preferential photodesorption of 12 CO. I'm going to skip this one, but there's basically 13 CO has about 21 wave number higher 0 point energy than 13 CO or 12 CO. Same deposition as before to make the ices, but we used two mixtures with different isotopic compositions, a 4-to-1 ratio of 12 CO to 13 CO, and then 3-to-1 ratio of 13 CO to 12 CO. We did it at 4 different temperatures, 10, 15, 20, and 25 Kelvin. We irradiated the samples for between 6 and 10 hours using a hydrogen discharge lamp that simulates protostellar emissions. During the irradiation, we monitored this whole suite of different chemical species to get both the fractured components of CO in the mass spectrometer and then also contaminants. So by measuring oxygen and CO2, we keep an eye on any sort of atmospheric contamination. This is just UV spectrum of our emission lamp, and at the pressure we were running the lamp, Lyman alpha is about 20% of the total emissions. But this is one of the plots that basically summarizes the results. We subtracted the background partial pressure ratio or partial pressures of 12 CO and 13 CO from those partial pressures during irradiation, corrected the 12 CO signal for any nitrogen contamination because they share the same mass to charge ratio, so there's an interference there. We normalized the enriched isotope in the mixture by the initial 12 CO to 13 CO ratio, which was obtained by FTIR. We smoothed the signals, and then we determined these partial pressure ratios by averaging the partial pressure across the interval of irradiation. And Yeah, I think that's just about it. The only thing I wanted to point out here is that you see the spike starting at the beginning, right when irradiation begins. The pressure spikes up, indicating that photoabsorption is occurring, and then when the lamp is turned off at the end, it drops back down. Yeah, we found preferential photoabsorption of 12CO across both mixtures and all temperatures. There was no apparent dependence on temperature or ice composition, and the highest partial pressure ratio, that's a typo, it should be 1.69 plus or minus 36 as the plot shows on the right. That was the highest average, is the one that's in text. But yeah, so that basically means that effectively 1.69 12CO molecules get photodesorbed for every 1 13CO. So the conclusions there are measurable between both thermal and photoabsorption conclusions. There are measurable significant differences in the binding energies and sublimation temperatures. This indicates that there might be interactions between ice and gas phase that influence the isotopic composition, even under small temperature differences and low temperatures. And through photodesorption, the preferential photodesorption of 12CO over 13CO may be a means of enriching 12CO in the gas phase, and could possibly, in part at least, explain this heterogeneity among YSOs that Rachel was talking about. And we had planned to do stuff with water and CO2, but COVID happened. Okay, so yeah, sorry I ran over a little bit there.
No worries. Thank you, Lucas. We'll go on towards our next talk, and then we'll have our Q&A after it's finished. So Donna, if you want to presentation, Dr. Danna Qasim is a postdoctoral researcher at NASA Goddard Space Flight Center in the astrochemistry laboratory. She is predominantly an experimentalist with an interdisciplinary background that touches upon interstellar to solar system chemistry, which she will discuss further in her talk.
Okay, can you hear me?
Yep.
Okay, great. Thank you, Danielle. And thank you for having me. So I specifically wanted to introduce myself here because my background is strongly in interstellar chemistry, but I have done origins of life research. I'm moving into solar system science in my postdoc. And so I just want to assure the audience that I do care to connect interstellar deep space chemistry to the more evolved stages of the stellar formation cycle, like our planets and the early Earth. So in my master's, I investigated the reactivity of a meteoritic mineral called schreibersite, which is Fe2NiP. And this is relevant to early Earth chemistry and how schreibersite could have contributed to phosphorylation reactions on the early Earth. This was in collaboration with the Center for Chemical Evolution, and we were specifically trying to understand the role of the mineral surface in these phosphorylation reactions. And what we found was that the surface was rather, it was not a dead surface, but rather a chemically active surface. In my PhD, I then went back in time to investigate the formation of interstellar ices, and this work was strongly tied to astronomical observations and was quite useful for some accepted proposals for the James Webb Space Telescope Cycle 1. And now for my postdoc, I'm largely investigating the combination of both meteoritic minerals and ices and adding hydrothermal processing in there to understand how hydrothermal processing of the residues of irradiated interstellar ices affects the distribution of amines and amino acids in meteorite parent bodies. But today, I'm going to talk about another postdoc project of mine in which this work is submitted, and it's a quantitative and also a qualitative study on how radiation, so like cosmic rays, can affect the D to H ratios of organics in interstellar relevant ices, and then how that data can be used to interpret the D/H ratios of organics observed beyond the interstellar medium. So I kind of want to expand on the idea of how interstellar materials, like interstellar ices, can be important to understanding the origins of life on the early Earth. So why should the origins of life community care about interstellar chemistry? And I think that there are at least two big reasons. And one reason is that in interstellar space, that's where our molecular cloud is. So our sun, the planets, the moons, they all came from that molecular cloud in the interstellar medium. And so they inherited the chemistry that was in that cloud. And that cloud is rich in chemistry, which was not thought of some time ago. So not only are there simple molecules like water and ammonia, but we know from astronomical observations that there's also chiral molecules, amines, aldehydes, aromatics, and so on. And these are observed at really low temperature, low pressure regions. So to give a more specific example, it's been known that comets delivered organics to the early Earth, in which a fraction of those organics is preserved interstellar materials. And this is further supported by all the recent papers about Comet 67P from the Rosetta mission. And there's a nice review paper from the PI of the Rosina instrument, which highlights the notion that interstellar chemistry is linked to solar system chemistry and even to life on Earth. So another big reason why the origins of life community should consider the role of interstellar chemistry, and this, I guess it kind of goes back to the comet example, is because there is evidence in the literature that interstellar materials are distributed beyond the interstellar medium and are more or less pristine. So I just kind of scanned through the literature and found some examples. So in this study, so it was found that the protoplanetary disk was just too warm for methanol ice to be formed, since methanol is formed from very volatile molecules and atoms, as Lucas kind of mentioned. But they detected methanol in the disk and found that it was methanol inherited from interstellar space. And what makes this exciting is that methanol is key to the formation of more complex organics. The astronomer's definition of complex, which is methanol is a complex organic molecule. But anyway, so there's likely more complex interstellar organics in that particular disk. Cassini data, and I think also Voyager data, showed that the D/H ratio of methane in Titan's atmosphere is about an order of magnitude higher than that of the gas giants. And this deuterium fractionation typically indicates interstellar inheritance. And again, methane may not be so exciting, but it's a precursor to larger organics. And so these larger interstellar organics may also have made their way to Titan. And then in this study, they detected high amounts of D2O towards young stars, which again strongly indicates that the water observed is largely pristine interstellar water because it's largely deuterated. And of course, finding the water trail, tracing the water trail is important to understanding where life could be in the universe. And then there were some recent studies on chondrites where they found that the variations in the D/H signatures of water and organics in those different chondrites are more likely to be dictated by the interactions between the interstellar cloud and the disk rather than meteorite parent body processing. And again, that's showing that interstellar materials can remain intact and not be significantly processed when traveling across our solar system. So from this, I highly encourage that when you do your origins of life research, to consider reaching out to one of your fellow interstellar astrochemists, because yeah, even if there aren't direct applications of interstellar chemistry to your work, it never hurts to make a new contact and have a conversation. So now that I've hopefully convinced you why it's important to tune into interstellar chemistry research at least once in a while, I'm going to continue talking about our work on how radiation can impact the D/H ratios of organics and specifically aliphatics in interstellar relevant ices. So as I had mentioned before, an enhancement in the D/H ratio of any organic or water across the solar system can be indicative of interstellar inheritance. And so this kind of goes back to the Big Bang, which is responsible for the original formation of the light elements, such as hydrogen and deuterium. And specifically with deuterium, there are no known sources that can produce and maintain ample deuterium. So any heterogeneity in the D/H ratio is reflective of the local physical and chemical processes. And so we see that particularly in these low temperature dense molecular cores where deuterium fractionation is enhanced because of deuterium's lower 0 point energy. And actually this deuterium fractionation is even further enhanced in these cores because of not just low temperatures, but there's also gas phase and solid state chemistry that increases this enhancement. I'm not gonna go into that chemistry here, but essentially, so low temperatures and chemistry cause a good amount of deuterium fractionation in interstellar space, but there are also other processes such as radiation that can alter the D/H values, and that has not been well studied in the lab. And so specifically, cosmic rays are everywhere, omnipresent in the universe, and can penetrate through almost anything. So here we studied how cosmic rays can contribute to altering the D/H ratios of aliphatics embedded in water ice. So in this work, we measured the D/H exchange rate constants for 4 aliphatics. So we looked at methane, deuterated methane, ethane, and deuterated ethane. And then we just qualitatively discussed the cases for deuterated acetylene, ethylene, and deuterated ethylene. So I'm just going to run through a short experimental procedure on how we study, for example, the D/H exchange between CD4 and H2O to yield CD3H. So we start off by cooling our sample to 20 Kelvin, which is at the higher end of an interstellar grain temperature and at the very much lower end of solar system environments. And the plan is to move to higher temperatures to also cover more solar system relevant temperatures. We then create a 50-to-1 3 micrometer thick ice, and that's measured using laser interference. So the 50-to-1 is chosen so that we have the highest dilution factor without drowning the signal of our organic. And 3 micrometers is chosen because it's below the penetration depth of 1 MeV protons, and it's also thick enough to give us a good signal to noise. And then the magic happens. So we irradiate our ices with 1 MeV protons that are accelerated by this huge Van de Graaff accelerator. After the ice gets irradiated, we collect our infrared spectra, which ultimately allows us to observe the loss of the signal of a vibrational mode of CD4 and the growth of the signal of a vibrational mode of CD3H. And the way that we measure the amount of reactants and products is through doing additional experiments to obtain what's called band strengths, also as Lucas had mentioned. And this, so band strengths, they essentially give you the strength of your vibrational band and can be thought of as a calibration factor. So the main focus of the study is to obtain the radiation-induced rate constant at which D and H are exchanged between the aliphatic and the water. So for this study, we made the assumption, a pretty fair assumption, that the reactions follow a parallel or competing first-order trend. So in the example case of CD4 and H2O, A is CD4, B is CD3H, and P is all other products that are made from CD4. And what we really care about for this study is K1, which is in units of inverse megagray, and that's a inverse unit of radiation dose. But K2 is also helpful for understanding specifically our percent yield, which I'll talk about in the next slides. And then, of course, so we use this integrated rate equation, which you can just find in a textbook for parallel first order reactions. We did add the constant C at the end of the equation, and that kind of accounts for experimental hiccups that are kind of hard to avoid. So it takes into account any features in the data that we may mistaken for spectral features of the formed product. So with our column densities of the reactants and singly deuterated proteated products, as well as the radiation dose, we were able to obtain the rate constants by using a nonlinear least squares routine. All right, so here's the table of the radiation-induced D to H exchange rate constants in our aliphatics, which the goal of this paper was to measure these rate constants. And to the right is essentially the steps for the chemistry of interest taking place in our experiments. So yeah, it kind of just gives us an idea of how the singly deuterated proteated molecules are formed. All right, so some of the highlights from this table are, so one, the rate constant for which methane is converted to its isotopic form is essentially the same as the rate constant for which ethane is converted. Another way to look at this is that the saturated 1 carbon molecule has the same rate constant as that of the saturated 2 carbon molecule. So with these saturated molecules, an H or a D gets kicked out either by an OD or an H, or by an OD or an OH, and then a D or an H is added, and then that's it. So that final singly proteated or singly deuterated molecule is not going to further react because it's stable. And since the rate constants are determined by the abundances of the reactant and product, this saturation effect likely explains the similarities between the rate constants of methane and ethane. Another highlight is that the D to H exchange rate constants are lower for the deuterated organics than the non-deuterated organics. This isn't really surprising because if you follow the chemistry, you'll see that in order to make the singly deuterated proteated molecule, you need to abstract a hydrogen or deuterium atom from methane or ethane. And the CD bond is stronger than the CH bond because of deuterium's larger mass. So the D to H exchange will be slower for deuterated molecules because it requires more energy to break the CD bond than it does to break the CH bond. So it was kind of difficult for us to get a percent yield of the singly deuterated proteated molecule for methane and ethane because there's a lot of spectral overlap in the infrared data. But we were able to find isolated features that allowed us to at least measure the percent yield of CH3D from CH4. And from those features, we measured a 75% yield. So that's a pretty significant yield. And that actually lines up with our very small value for K2. So K2, again, that's the rate constant for which the organic, so like CH4, turns into anything besides CH3D. And we got a very small value of practically 0. So again, that means that CH4, so most of the CH4 has been converted to CH3D rather than any other molecule that CH4 could convert to, like methanol or doubly deuterated methane and so on. And then, so we did study acetylene and ethylene in water matrices. And I guess it's not like totally surprising that with our techniques, we could not probe the D to H exchange. And a big part of that is that those molecules are really reactive. So for example, if there is D to H exchange with acetylene, what happens is that that singly deuterated proteated acetylene will eventually react with something else, which I was able to catch it in the data. Also, the addition of hydroxyls to acetylene and ethylene, I think, is like almost barrierless, which is pretty low in comparison to abstracting an H or D atom from those molecules, which I think is like over 50,000 Kelvin or something. Which then, so that makes it even difficult to have D to H exchange in the first place. But this is actually interesting information because it tells you that if you have acetylene or ethylene in a water ice matrix and it gets irradiated, you probably won't have an efficient D to H exchange process just because there are other pathways that are just more favorable. So if you detect a singly deuterated or proteated acetylene or ethylene in space, you may think twice before tracing that back to radiation-induced D to H exchange in water ices. So as I had mentioned near the beginning of this talk, D to H ratios of extraterrestrial organics in general are used as tools to constrain the origin of molecules. So having these radiation-induced D to H exchange rate constants can be really useful because then you can put it into a model and actually see how influential this process is to shaping the D to H ratios that we observe in space materials that have been dispersed throughout the solar system, including landing here on Earth. You know, our experimental conditions, they don't exactly replicate the conditions in the interstellar medium. So there should be some caution when incorporating these rate constants into a model. And so one caution is that these ices are very simple. They only have one organic in a water ice matrix. Whereas in interstellar ices, like real interstellar ices, you'll have a variety of organics typically embedded in water ice. So I'd recommend to take these values as upper limits in a model, since in interstellar ices, there will be other organics that will compete for D to H exchange with water, which we would expect to then reduce. I would expect that it would then reduce the rate constant of our studied aliphatic in the laboratory experiments. And then another caution that I had kind of mentioned before is that these rate constants, they were obtained at 20 Kelvin, which is pretty low for solar system temperatures. But then again, you still need these rate constants to understand the D to H ratios of aliphatics across our solar system that came from the molecular cloud and that are minimally processed. And so, as I had mentioned, there's evidence of the preservation of interstellar materials even out to planetary satellites. And since our Earth and planets inherited the chemical ingredients from our interstellar molecular cloud, interstellar anything always has the potential to be applicable to what we observe today. So it's important to acknowledge these rate constants when understanding D to H ratios across our solar system. So I'm just going to talk about two examples of how these rate constants can be applied to understanding the D to H ratios of aliphatics in particularly meteorites and in comets. So with meteorites, it's been found that they can undergo processing in the meteorite parent body, such as aqueous alteration, which that process can change up the D to H ratios. But it's also been observed, speculated, that the insoluble organic matter in some of these meteorites, which they contain aliphatics, are thought to be formed in the ISM, or the interstellar medium. And even the D/H ratios of this insoluble matter in some of these meteorites reflects largely interstellar to protoplanetary disk inheritance. So for the meteorites that do have preserved interstellar aliphatics like methane and ethane, it would not be surprising if they had similar D/H ratios, because both molecules are expected to be formed simultaneously in interstellar space and embedded in water ice. And then, of course, subjected to radiation. So if the D/H ratios are very different, then radiation-induced D/H exchange in ices may not be the dominant process. And then with comets, it's a little bit, well, okay, I won't say that. So with comets, the bulk nuclear ice is partially composed of pristine interstellar ice that's protected to an extent by layers of cometary material. So our results can be somewhat directly linked to the D/H signatures of cometary organics. So in the molecular cloud, there's actually a region where you have H2O ice. And then when you go into higher density, lower temperature regions of the cloud, you start observing more HDO and D2O ices. So in the comet, depending on what type of water is observed, it should be taken into account that the D/H ratios of the organics embedded in those water ices are likely to be partially reflective of radiation-induced D/H exchange between the organic and the water. Okay, so what should you take away from this talk? One thing that I hope sticks is that radiation-induced D/H exchange of stable aliphatics like methane and ethane is a pretty effective process. So that should definitely be included in models when we're trying to understand the D/H ratios of these aliphatics, especially if there's an indication for interstellar inheritance. Methane and ethane have similar D/H exchange rate constants when they're embedded in water ice. And we conclude that their stability as saturated molecules leads to similar rate constants. So these rate constants are also dictated by the CH-CD bond strengths, where the CD bond is more difficult to break. And so the deuterated versions of methane and ethane have lower rate constants. And then for more reactive aliphatics like acetylene and ethylene, it's speculated from the laboratory experiments that radiation-induced D/H exchange is probably not a very effective process in shaping the D/H ratios of these molecules, since they're so reactive to other processes, such as adding H or OH to the triple or double bond. So that's all. And thank you to NASA and CREST for funding me. And thank you to the organizers for inviting me.
Great, thank you so much. Yeah, so those are three great talks, and we have just over 15 minutes left. I saw that James just opened up the chat, and you're welcome to post your questions in there, or you can also raise your hand, and we will unmute so you can ask the speakers directly. So I saw Micah has a question, so I'm just gonna ask you to unmute. Should be able to turn on your mic.
Yeah.
Great.
So great. This is fun. You know, I haven't been on these for a while, and it's fun to come in and see a bunch of UHV work. So my question for both Lucas and Dana would be then, have you considered in your work the effect of the substrate? Now, I realize that a lot of ionizing radiation doesn't go that deep, but I think, you know, if you're talking about cosmic rays and UV, there's a potential for that radiation to reach the ice substrate interface. And I'm wondering if you've thought at all about how that could affect your results, and if you looked into using more representative substrates.
I'll just go first if you don't mind. Yes, so I think that's a great question. It depends. So some of the more volatile species, so it's been modeled that, like, for example, if you form water ice in the interstellar medium is formed by the accretion of H and O atoms from the gas phase onto the ice, onto the dust grain. And then CO freezes out from the gas phase to the ice. And so a lot of these volatile atoms accrete and create these molecules that are then just directly formed on the dust grain as an ice, more so than being incorporated into the grain. But there are, I believe that there's heterogeneous catalysis going on. And also there's this huge issue in interstellar chemistry and also in cometary chemistry of the sulfur depletion problem and the phosphorus depletion problem, where like the less volatile like sulfur and phosphorus is probably, we're guessing that it's actually like incorporated into the grain. And then there maybe some of that, when you have radiation coming through, hitting through the ice, it may release some of the sulfur and phosphorus. So I think it just depends on what molecules you're interested in. But essentially, I do agree that having that substrate, like more representative substrate, would be useful.
Great, Danna. Thank you. Rachel and Lucas, do you have anything to add to that, or you can go to the next?
I don't think I have much to add to that. I think that was a pretty great explanation. I will say that it's, in some instances, it's somewhat difficult to get a more representative substrate if you still want to maintain all of these different measurement techniques that you're using. Like in our case, for example, if we were to use like silica as a substrate, which would be more representative of a dust grain, then we couldn't be using IR transmittant spectroscopy, but the sapphire allows the IR beam to pass through without interfering with the measurement. But I'm not an expert on the interactions between the substrate and the ice with respect to the radiation, because my work was focusing on the desorption of the ices from the substrate, and mostly the upper layers of the ice. But the effects of the substrate, as I was talking about with the thermal desorption, like they are certainly there, especially when you're trying to get binding energies and sublimation temperatures.
Sorry, I just wanted to go off on what Lucas was saying. Like, it is technically challenging also to do that. I think a lot of people in the ice community, like there could be more expertise on that, because there could be heterogeneous catalysis going on, and that completely complicates the situation. So I think it's hard to incorporate a realistic substrate.
Thank you. Rachel, you were next for asking.
Yeah. Okay. Thank you. Yeah. And I don't have anything I'm an astrochemist, so I don't know. Observationally, I'll trust you guys. So this is a comment for Dana. And first of all, thank you for mentioning astrochemists as far in this group. There aren't that many astronomers, I think, in PCE3, or maybe there are more now. So I think it's great you talked about that, and especially meteorites, because also we don't think often, astronomers especially, and then getting these in discussion are really important. And I just wanted to comment about the heterogeneity. It's connected to heterogeneity, but inheritance from the cloud to the disk is still debated, and models kind of go back and forth, and inheritance has been part of this, especially the cosmochemistry community has been debated, is still debated even at current meetings like at METSOC. And I just wanted to mention too that with CO, in fact, just some new observations that I just actually finished looking at with some binaries, one has a disk and one doesn't, one pair, looks like we might see some additional signatures that it might be in the non-disk gas, like from from the cloud. And I just wanted to mention that CO, if you look in some of this cosmic chemistry literature, in addition, I mean, I wrote down the papers you mentioned, but like Steve Desch has models about, in disk models about inheritance, and Alexander Croat, and there are some really good papers on this, and to think about also these other molecules like CO, but it's looking like there's a lot of support now for this inheritance versus the disk. But I just want to caution that it's not concluded in any way yet about whether it's in signatures that are in the disk versus not, and especially with YSOs, because we have very single little tiny bits of data. So, but it's really interesting, and I just wanted to comment that it was good you brought that up, and to consider these other molecules too. Thank you.
Yeah, thank you. I have a question back, but I know there's so many hands, so I'll wait.
Oh, okay. You could also email me if you want.
I think you can go ahead. We've got 9 minutes, so if you have.
Okay. I just wanted to, kind of a general question for Rachel and Lucas is, do you think that with the inheritance studies and also just fractionation in general, do you think that JWST will have a role in helping us better understand fractionation, and also helping us better understand what is inherited by the disk from the cloud?
That's really good. It's a good question. I think there are a lot of different types of observations that go into that, and also theoretical models that look into that. I will say with the ground-based observations, the advantage of those are that we have these really high resolution, very high resolution mass spectrometers on these ground-based telescopes. So VLT is one, Keck has one near spec, but that's only 25,000. And then IRTF, while a smaller telescope, so you're limited to to these bright YSOs, the resolution is 80 to 85,000, which is really good for CO. And we need that high resolution and a large enough mirror in order to get precise isotopic abundances of these molecules. And I say that because JWST is going to open up windows into the universe and exoplanets and atmospheres. But if you're asking about isotope ratios, looking at CO, and I would say even with D to H, I don't know off the top of my head the type of resolution, but the problem with water is that you get either really saturated or not enough. And so you have the saturation with the main isotope log of water. And the same is true with CO2. So CO ice as well, is that you get saturation of the main isotope log, and then the 13 CO kind of has to fit, so you have this very small window of column densities. And so I don't know, so with AWST, we're not going to have the spectral resolution, but that said, it could inform other models. But the abundance ratios, looking at 12C, 13C, and oxygen, we need these high resolution ground-based telescopes to get the precision in absorption, to get the precise abundances that then you can compare to meteorites in some meaningful way. So I'll just say that about ground-based. I don't know if Lucas I don't know how much Lucas wants to add on that or anything. That's a good question.
I can't really add a whole lot of observationals, not my thing really.
Great. Thank you. So Kevin has his hand up. I will ask you to unmute.
Okay, yeah. Thank you, Danna and Lucas, for two very interesting talks. Just wondering about this D to H and carbon-12, carbon-13 isotopic ratios. Can they be used, like in our solar system, to predict the sort of long-term history of different solar system bodies, such as Titan? Because if you look at other solar systems, we're seeing something quite strange, like large sort of gas giants in close proximity to the parent star. It's quite different to the arrangement of planets in our solar system. Now, if I was to sort of hazard a guess, I would say that the D to H and carbon-12, carbon-13 ratios are D to H and carbon-13 to carbon-12 ratios are much smaller the further out you go in our solar system, say to the Oort cloud. So the Oort cloud bodies, including comets that remain in orbit at those distances, are they much more abundant in the lighter isotopes? And can this therefore be used to predict the sort of history of different solar system bodies in terms of relative positions with respect to the parent star? Are they sort of been in various distances from that star throughout the history of the solar system since the planets sort of condense from the protoplanetary disk?
Yeah, I guess I'll go first. That's a really good question. I think I don't know how to fully answer that. It's a big question. But I don't know if there's like maybe a simple, or not simple, but like a linear way of seeing it. Like, so for example, with Titan, so Titan's D to H ratio, I think is like 10 to the minus 4. But then I think with Saturn and the other gas giants, it's like 10 to the minus 5.
Mhm.
And so they're kind of in, like, I don't know, close proximity. So why does Titan have 10 to the minus 4? So for me,
it's an order of 10,
yeah.
magnitude of 10 out, actually. It's quite interesting. Here
Yeah,
on Earth, it's one in 1,000 is of hydrogen is deuterium. That's what it is. It's 10 to the minus 3 here. That's what the ratio is here on Earth.
Yeah, and I actually see Rachel's comment. She said, "I don't think that there's a spatial correlation," and I don't think there's a spatial correlation. I also think that the D to H ratios are still I think there's still a debate as to like what all the D to H ratios are. But yes, I agree that there probably isn't a spatial correlation with the ratios.
What about comets that have varying orbits, which could take them in close proximity to the sun? I would have thought there'd be a sort of a higher D to H ratio there, like Halley's Comet, for example.
Can I just mention, there's a plot, and I was actually going to try to find it. There's a plot I used for my class. It looks at D to H, and it may not be so current, but it's at least a few years. So they have Jupiter family comets, Halley type comets, and the rest, and some other bodies in the solar system compared to Earth, looking at D to H, and Comet P Hartley 2, which is, I think, one of the first, if not the first. And I don't think there's a spatial correlation. It was mostly looking at D to H just compared to Earth to talk about origin of our oceans. And I was going to try to find the plot, but it was, I don't know how to pronounce it.
Is it Ilsa?
No,
Ilsa
it was Hsay, H-S-I-E-H, I think. I can find it probably in a minute. But anyway, I just want to mention that the spatial correlation is a really interesting question. I also don't think YSOs are going to inform that necessarily in terms of the solar system. We're looking at kind of different things, but these spatial correlations, to my understanding, they're not established.
So the closer you are to the parent star, more radiation, you've got more UV and cosmic radiation acting on, especially any sort of icy bodies like comets,
Yeah. Right. You think about CO self-shielding, though, that could affect isotope ratios if you're thinking of the gas and the YSO. And so we have to consider that too. And that was part of the exploration looking into the ice, is to see if that it's harder to establish mass independence though with fractionation, because you only have 2 isotopes.
Great, thank you so much. We have 2 minutes, so I'm just going to quickly ask Christina to unmute for your question, and then I think we'll be done.
Hi, can you hear me?
Yeah, you're a little bit quiet. But...
Okay, I'll just talk louder. Thanks so much for the talk. This was really interesting. So I have a question for Lucas. So if you're using a hydrogen lamp, you're going to probably see some sort of photochemistry happening within your ices. Are you monitoring photo products at all?
Yes, that's a great question. So yes, we are. And that was the reason why we were so careful to make sure that we were measuring oxygen through the mass spec as well as CO2. And I probably should have included it in my talk. We were also monitoring like evolution of CO2 ice throughout the irradiation, which there wasn't any noticeable buildup. So that was kind of like a check for us, because you can of course get photochemistry between oxygen and CO to produce CO2. We were measuring both 13 and 12 CO2 with the mass spec. We didn't see any significant increases throughout the course of irradiation. But out of curiosity, one time after irradiation was over, I ran the mass spec as I was just heating up the system to cool down after the experiment was done, just warming everything back up to baseline and measuring the mass spec just out of curiosity. And I came across quite a few photochemical products, including formaldehyde, and I think ethanol was one of them in there. But yeah, so we did see that weren't there when I would do the same thing and heat it up during a background experiment when there was no irradiation. So we did see some photochemical products for sure.
Great, thank you so much. So we're reaching exactly 2:30. So I saw that James posted the link to the PCE3 Slack channel in the chat. We can continue the discussion there for any questions that weren't answered in the seminar today. I just wanted to thank all of you for attending and the series, and a special thanks again to our guest speakers, Rachel, Lucas, and Donna. They were great. And thank you so much to the PCE3 co-leads and the co-organizers for their continued support. Our next seminar will be on Thursday, December 9th, and that will be our last session of 2021, and we'll regroup in the new year for our next round of talks. So yeah, so we hope you have a great rest of your day. Thanks for attending, and we'll look forward to seeing you again in 3 weeks.
Thank you, Danielle.
Thank you.
Thank you.
Bye.
Thank you.